Hello everybody, my name is Lee. Today I'm going to be uh, presenting about the Gibbs free energy from a standard molar enthalpies and a standard molar entropies at a non-standard pressure. So here's just on the right side is just going to give you a little bit of content of what I'm going to be going through. So the first one I'm going to be doing an introduction, sort of just like a review of what we learned previously in class. Second one is about like relevancy of how it's used in our daily lives. Third one is basically the rules and equations of we're going to be going through equations, knowing about the names and units of it, and also we're going to be doing a little bit of at the end we're going to be also doing little bit of problem solving. So here we go. So first of all, we're just going to be doing a little bit of review. So Gibbs energy was developed in 1870 by Joshua Willard Gibbs. Basically, he was an American. That's why I had a flag and an eagle up there to represent him. And he originally termed his energy as available energy in the system. His paper published in 1873 called Graphical Methods in the Thermodynamic of Fluids, that was outline of how his equations could predict the behavior of a system when they are combined. This quantity is the energy that associates with a chemical reaction that can be used to do work, and it's actually the sum of its enthalpy, abbreviated by the letter H, and the product of the temperature and how entropy, which is abbreviated by the letter S, of the system can predict the directions of chemical reactions under two conditions. It's under constant temperature and constant pressure. So as you can see here, G is equal to H minus Ts, and if delta G is smaller than 0, it is a spontaneous reaction, and if delta G is bigger than 0, it is called a non-spontaneous reaction. So let's go to the next one. So why should we care about this? So, I mean, is it helpful or useful in daily lives? Well, actually, yes. Well, Gibbs free energy is important in biology research because it enables one to predict the direction of a spontaneous change for a system under a constraint of constant temperature and pressure. These constraints generally applies to all organisms. Basically, free energy is vital in all cellular metabolism as it indicates which biochemical pathway are viable for cellular functions. By analyzing free energy changes across reactions, scientists can predict metabolic flow and identify the key enzyme that regulates these pathways. This understanding not only aids in grasping how cells utilize energy efficiently, but it also provides insight into potential targets for drug design and metabolic engineering. As you can see here, I put on the left side, I put photosynthesis, and on the right, I put cellular respirations in human beings. So by understanding that, we could actually come up with a drug or a cure to help solve a certain type of problem. It's also used in other different types of procedures too, like industrial synthesis of how they are able to make ammonia out of high pressure. It's also useful in environmental science, basically to see gas phase reaction in the atmosphere, and it is also used in battery operations as well. So let's go to the formula. So Gibbs free energy at a non-standard temperature, as you can see here. Let's say we have a reaction A plus B, an equation, equation A plus B goes to C plus D. So here in the following equation, we have for the non-standard equations, we have delta G is equal to delta G O plus RT ln of Q. Delta G is basically a free energy at any moment. Delta GO is a standard state energy, free energy, plus R is basically the ideal gas constant, is equal to 8.314 joule per mole Kelvin. T is temperature measured in Kelvin. And ln Q is basically quotient reaction. It's basically if they gave you a molarity, it would be molarity of product over molarity of reactants, but if they gave you pressure instead, it would be the pressure of the reactant over the pressure of products. So it can be both ways. Oh, and also, let me show you, before we go in any further, I wanted to show you the standard um, free energy change. Basically, sorry about that. So basically, delta G is equal to delta H minus T delta S. So what does this mean? So basically, delta G is the change in free energy, delta H is the change in enthalpy, T is temperature, delta S is the entropies change, or I should say the change in entropy. There you go. Oops. Entropy. I believe that's how it's spelled. Hope I'm right. Alright, so the units of G would be in Joule. Delta H would also be in Joule. T would be in Kelvin. And delta S entropy would be in Joule per Kelvin. That would be the units of all the standards Gibbs free energy in the reaction. Alright, now once we understand all the equations and how Gibbs free energy works at a non-standard and standard reaction, let's consider doing this following problems. So here in this problem, we are given a set of equation, and the first questions asks us to calculate delta G 0, which is the change of oops. Oh, what happened? Alright, now once we understand the Gibbs free energy at a non-standard and a standard Alright, now once we understand the Gibbs free energy at a non-standard and a standard reaction, let's try and solve some work problem. Alright, so here in example 7, we are given a set of equation, and the first one, use the thermodynamic data in the appendix to calculate the standard state free energy at 298 Kelvin. And then the second one is asking us to solve for the free energy at any moment for a mixture of all of these pressure that were given to us. So the first one, what we would do is we could look up the table. You could actually search it up in Google or in textbook. I prefer Google because it's way faster. And for this one, for the sake of practice, we're not going to be looking for the standard state free energy value of each of the elements, but instead we're going to be doing it from scratch. So let's do it. All right, so let's solve for number 1. It says to use the table. It says here. All right, so number 1 is use the thermodynamic data to calculate or to find delta G0. So we know that delta G0 is equal to the sum of G products minus the sum of G reactant. 0 right there. And we know we have this equation, so our equation was this: 4NH3 plus 5O2, 6 water molecule, and 4 nitrogen monoxide. There we go. So what I would do, if you want to do like an easier way in this problem set, you could actually look it up on the table. Like I said, it'll tell you the value of each of the molecule, but for the sake of practice, we're going to be given a table of delta H and delta S to then solve and find delta G0. So I'll just skip the video and come back with a table. Alright, so this is our table value. So to calculate for each, it would have to be... Alright, so we're given the whole set of everything, delta F and S. So here we find the changes of enthalpy for the reaction. So basically it would be the reactant side minus the product side. So that's what we're gonna do. So first of all, first calculate delta H for the reaction. And also when calculating, be aware of the number of coefficients on the equation, because it's going to be important when we're trying to solve for it. So here, reactant, I'll just write the whole thing down, is equal to sum of H product minus reactant. Product minus react, like that. So our product side, we have 6 molecules of water and then 4 molecules of nitrogen monoxide. So it would be 6 times the number of what's given to us in the table. So here we have, for water, we have negative 241 times 818. So write that down. 6 times negative 241, 818, plus, I forgot to put, there you go. Plus 4 times 90.25. 90.25 minus the product side, which is basically the same thing of what we're trying to do. Just gonna write there. So on the reactant side, we have 4 ammonia and 5 oxygen. So let's start off with ammonia. We have 4 times the table that was given to us is negative 46.11. So negative 46.11 plus 5 water. So 5 water molecule, 5 times 0 is equal to 0. And do the math for it, we would get a total of 905. Yeah, 905.47 kilojoule per mole. Alright, so that's the first one. We get our change in enthalpy. Now let's try to figure out, so calculate the change in entropy for reaction. So this is basically the same thing, same rule and same formula. We look at the equations that was given to us, and then we'll see, and then we take the product side minus the reactant side by looking at the table that was given to us right here. So let me So this is what we have. So we have delta H, which is basically negative 905.47 kilojoule, and we have delta S, which is equal to 8.5 joules per Kelvin. And if you want, you can actually convert delta S, or the change in entropy, to 0.15. There you go, kilojoule per Kelvin. There you go. And then when we have the change in enthalpy and then the change in entropy, we can now find the Gibbs free energy of standard reaction. So delta G0, that's what I called it, is equal to delta H, the change in enthalpy, minus temperature times delta S. Then that would be equal to 905.7 kilojoule minus 298, which is the temperature that was given to us at the beginning, 185. We should get about negative 959.25 kilojoules. So this is our Gibbs free energy at a standard reaction. So then, let me add another page. So from this, we now can actually find this delta G of at a certain moment. So as we remember, delta G of a certain of a non-standard would be delta G of a standard plus RT ln Q. Alright, so we have the Gibbs free energy at a standard time reaction, and then we know the ideal gas law, and we know the temperature. All we have to do is find Q. So how do we actually find Q? So Q is the quotient. Like I said, it would actually be the concentration. For example, we have this reaction, A plus B goes to C plus D, so reaction quotient would be the product C D over the reactant, so it would be concentration of A over B. Or if pressure was given, Q could also be the pressure of reactant, so PC. The pressure of products. Pressure of products, which is PC times PD over PA times PB. So in this case, we are given pressure instead of concentration, so we are choosing this equation. So we plug that in, plug everything in the equation, we should get something like this. So G you know what? To make it easier, let's find the reaction quotient. Yeah, that's what I said I was about to do. So Q is equal to P of water, there you go, times power 6, the products, and P of NO over 4 to the power 4, and over the reactant, P pressure of ammonia, pressure of oxygen to the power of 5. There you go. It was given to us, so all we had to do was to plug everything in. We had each values of it, so I'm just going to plug it in. Boom, there you go. So if we solve for Q, we should get about 1.47. I would just write 48. So this is what we got, and bar, or equal to 1.48 atmosphere, because they're the same thing. So note 1 bar is equal to 1 atmosphere. So there you go. So there you go. There you have it. And when we basically have everything we need, so let's go back to solving our original problems, which is the change of Gibbs free energy at a certain time is equal to Gibbs free of standard plus RT ln Q. We know what Q is, we already have it. So let's plug the whole thing into the equation. We would get is equal to delta G. What's delta G? So it's negative 959.25 plus R, which is 8.314, I guess, joule per mole Kelvin, times T. T was given, it was 298 times ln of 1.48. Yeah, there you go. So let's see, before we try to solve the whole thing, we are really looking at the units, make sure they match. So here found out that the units didn't match. So what I would do to make it match is to write it down here. So divide 8.314 joule per mole Kelvin by 1,000. Let me do it this way. So divide by 1,000 joules. Oops. So 1,000 joule is equal to 1 kilojoule. There you go. These cancels out, and then you get kilojoule, which matches this one, the delta G of standard. So there you go. And I'll write the whole thing again. There you go, plus 8.314 times 10 to negative 3. There you go. This time the unit should match. So yeah, side notes. Every single time when you're trying to solve for an overall change, make sure the units match. If it doesn't, that means you'll get a different answer. There, and kilojoule, mole, Kevin. So this is 298 Kevin, ln 1.48. There you go. So basically this right here let's do it step by step. This right here would be equal to 2.48, and this right here, ln 1.48, would be equal to approximately 0.39. Sorry. Here you go. So overall, we should get 959.25. So make sure they cancel out. So we have kilojoule. Oh, so no, that's not the one. It's joule cancels out. So we have kilojoule per mole. That's the only unit left. Plus them together, we would get so the total, so 2.48 times 0.39 would be equal to 0.97, I'd say, is equal to 8.29 kilojoule. There you go. So this is the answer for our equation. Yeah, this reaction, so since this, as we know from the beginning, less than 0, so this is a spontaneous reaction. Now that we know how to solve problems, if you want to solve a bunch of more problems, here's my reference. You can check them out in chemistry library texts or the introductory chemistry. These are great sources if you want to learn and try out new problems. So thank you for watching.